So I need to steal some of that for my, put it in my smartboard. So you can, so let's see, where am I? Right here. Some of you, I think, had already done this. So you, okay. So as I just said, this is a product. So I could write it like this just to fit it into a nice form. Use h of x just because then I can use f of x and g of x. So f of x is equal to x squared. G of x is equal to e to the minus x. So then you calculate f prime of x and you calculate g prime of x, and then the product rule says that the derivative of the product is not the product of the derivatives, but it's going to be equal to f prime of x times g of x plus f of x times g prime of x. And everybody knows what the answer is there. So the only thing we have to do is, what is the derivative of e to the negative x? Anybody know what the answer is? What's the derivative of e to the negative x? Yeah, negative e to the negative x. And you can use the chain rule because u of x would be negative x, so you'd get negative 1. That's where the negative sign comes from. So what I would suggest is just remember that the derivative of e to the x is e to the x, and the derivative of e to the negative x is negative e to the x, because you see it enough that it's such a trivial chain rule problem that you might as well just remember that. So then we plug them in. So we just get x squared times negative e to the x plus, actually that was the wrong order. That doesn't really matter, but I'll be consistent here. So it's f prime of x times g of x plus f of x times g prime of x. And the only thing you have to do to simplify it, I mean, you could factor out an e to the minus x, but if you gave it to me in this form, I'd be happy. But you could factor out an x e to the minus x, and that would leave 2 minus x. I think looks right. Okay. The next one is just using the chain rule. So this is u of x. This is f of u. Yeah, I saw that on. It reminds me of something I saw on. It might have been on. I watched the thing from Saturday Night Live. I think it was the Daily Update or something like that. Trump is on his thank you tour, and Hillary Clinton is on the FU tour. Trump, huh?
Trump tweeted after that the other night.
Did he tweet after that?
Like SNL is unwatchable. It's ridiculous or something.
Yeah. Yeah, Trump said the day after he was elected that he was going to be restrained on Twitter. I don't think that happened. So I might just, change it to f of x, and and then f of, using the chain rule, f of u is e to the u. U of x is equal to x cubed plus 4x squared plus 5. Three x squared plus 8x f prime of x is f prime of u times u prime of x. Notice I'm putting a parenthesis here because if I don't know if I'm multiplying just by this or I'm multiplying the whole thing. Well, you probably know that, but if I was reading it and I just looked at that one statement, you always have to think about, you know, if I have a math statement that's in, what's the word? Anyway, by itself, and nothing else is around it to use context for, would I be able to interpret it correctly? And so that's why we would include the parentheses in there, even though you probably would know what you're doing. And so I would change the order. So I would get e to the u, plug u back in, and I get that. Okay, those are all easy things. Did we do this one? I don't think we did. So this is a definite integral. So I want you to, you know, redefine the limits in terms of u. Don't plug u back in terms of x, because it's not necessary. So in this case, u is going to be equal to x divided by 2. And remember that the derivative with respect to x of a to the x is equal to the natural log of a times a to the x. So you just have that extra term compared to the when a is e, then you just get e to the x. So I'm going to let you work on that one for a second. If anybody has any questions about what to do, let me know. I will. Oh, why am I showing the derivative? That's a good point. We're integrating. You're probably wondering why I said that. I don't know why I did that. Okay. The other rule is the integral of a to the x dx is equal to 1 over the natural log of a times a to the x plus c. Of course, we don't need c because it's not an indefinite integral. It's a definite integral. So don't put c down anytime you have a definite integral. That happens sometimes. You know, you get carried away and you forget that you don't need it for a definite integral.
This is the one that we skipped.
Oh, is that one that we skipped?
We tried the u of x over 2, but then it's just 1/2.
Yeah, that's fine. So then you just get du over, or du times 2. So dx is equal to 2 du. And you just factor out the 2. And then you just use the rule. We get used to dividing by the constant whenever we have a constant, but in this case, well, it's mostly because the exponent is not 2x or 3x, it's x divided by 2, so the dx part becomes 2 du instead of du over 2, but it's treated the same way. Get your calculator out so you can calculate it. That's not a problem with my calculator. Oh, it is. Is that what you got? Caleb, did you get that? Kenzie? Yep. Okay.
Why do you do 1 over ln 4?
Because the formula that we originally came up with, because the derivative of a to the x is the natural log of a to the x, the integral of a to the, you have to divide by the natural log. So it's just when you use the derivative to get the integral, you have to divide by the natural log. Okay, did we do this one? Seems familiar. I guess not, nobody's saying we did. So what you're going to let, because the exponent of e to the x is not just x, in this case, we would let u equal the exponent, which is 3 times x to the minus 1 power. And you should get something close to that, what's left over, except by a factor of 3 difference and a negative sign. And remember, you're going to redefine the limits and don't substitute back in. So when when x equals 3, u equals 3 divided by 3, which is 1. And when x equals 1, u equals 3 divided by 1, which is 3. So they switch, sort of. And there's no reason why you can't integrate the other direction. So we normally, yes. Let me look. I just looked a few seconds ago and I didn't see it unless it's, so there's public, see it says staff, notice it says X. What does that mean?
Here, let me check it real quick.
Okay.
Is this crucial to your class, or can you go on without it? Or?
I can go on without it.
Oh, okay.
I'm recording it using another means. Yeah.
Give us a call real
Yeah, it's 9 o'clock. Can you come by at 9 o'clock?
quick. Yep, I'll do that.
Yeah. Is it working for you?
Yeah, we've got it up. I'm just gonna have to change a few settings. To get
Okay. Okay. So I went to bed at about 10:30 on Saturday night. Third quarter, we're down 14, and then we just had given the ball back to him, and I said, no, this is the Hokies. Virginia Tech, Saturday night. So then I was with church, and I saw somebody who's a Virginia Tech grad, and I said, so how bad did we do? And he goes, actually, we almost won. I know. I was like, I'm not sure what time did you watch the whole thing?
Yeah, it went off at about
12, yeah, that's too late for me. It's kind of it's a risk reward situation. I'm not sure if staying up to 12 was worth seeing us lose just by a little bit, but then probably he ain't going, woo! That would have thrown the whole college playoff thing into confusion, wouldn't it? Okay, so we have e to the u times du divided by 3 between 3 and 1. So this becomes e to the u. Dx over x squared, this is going to be negative, oh, this is a negative sign. So you get negative 3 times x to the minus 2 power dx, which is negative 3 dx over x squared. So to solve for x, dx over x squared. Now, I've noticed somebody doing it, and it's fine because I've seen, I know that this is the way they teach it at James River, and that this person does not go to James River. But anyway, another way of doing this substitution is you solve for dx instead of trying to get dx over x squared. So at this point, instead of doing this or solving for x squared dx is equal to negative du over 3 by dividing by negative 3, what you can do is you can actually just solve for dx. So dx is equal to du divided by negative 3x squared. So this is a, so what I would do is I'd multiply, is that right? Am I doing it the right way? No, I'm not doing it the right way. Sorry.
Dr. Nicholson?
Yeah.
Tyler's trying to watch it.
Yeah, I know. That's the problem. He's going to have to watch it later because I couldn't get on Collaborate. So
Okay.
yeah, just tell him to watch the recording later, which I'll post somewhere. I'll let him know. But yeah, that's why I'm recording it using Camtasia instead. Okay, so what you would do is here to solve for dx, we'd multiply both sides by x squared. So we'd have x squared du divided by negative 3. So when you go to substitute, you would have the integral from 3 to 1 of e to the u over x squared, and dx would be equal to x squared du divided by negative 3. And then you cancel out the x squared parts, so that it all becomes a part of, as a function of u. So you end up with e to the u du, and you factor out a negative 1/3, which is what we're going to do anyway. So it's just a different, you just solve for dx and then cancel out the term that's common instead of having to put it in a form like this where you have x squared over, well, I kind of skipped that step here, but if I had du is equal to negative 3 dx divided by x squared. What I do is I solve for that, and then I substitute in for that, which is going to be negative du over 3, and I get the same answer. Is there an advantage or disadvantage to either way? Probably not. So if you think that might be something you want to try out. Okay, anyway, back to here. So the integral of e to the u is e to the u, and we don't have to substitute back in because I've changed the limits. So you end up with negative 1/3 times e to the first power minus e to the third power. And then we take our calculator, negative 1 divided by 3 times e, where the heck is e? E to the first power minus e to the, delete, e to the third power. And I get 5.79. Is that what you guys got? Yeah. Okay, next one. So this is just using the chain rule. We had a previous problem where it was e to the x squared minus 2x plus 3, and the only difference is the differentiation formula says that the derivative with respect to x of a to the x is equal to the natural log of a times a to the x. So since we did one just like it, y prime using the chain rule, so the chain rule, this would be a to the u power. And the derivative of a to the u is the natural log of a times a to the x. So you end up with the natural log of 3 times a to the exponent, original exponent. Well, I'll just put it in here, a to the u. And then you multiply by u of x, the derivative of u of x, which is going to be 2x minus 2. And then you can plug u back in. So I let u equal the exponent. So you get the natural log of 3 times a, in this case, is 3 to the x squared minus x, 2x plus 3 times the derivative of the exponent, which is going to be 2x minus 2. And I would move this term to the second part of the expression.
Plus 2x minus 2.
2x minus 2. So where did I mess it up here? 2x minus 2. Yeah. Everybody okay with that one? And then the last one is you're doing the log to a base other than e. So all you have to do is this again, the chain rule, and the expression for the derivative of the natural log of or not the natural log, but the log to the base a, looking at my table here, is log base a of u is, it says u prime divided by the natural log of a divided by u. So I'm going to write this out because this is what I give you a copy of, I think, or you have it already if you can bring it in, to remember to bring it in. But if you look in the book, you've got the derivative of the log to the base a of u is equal to u prime divided by the natural log of a times u. So remember, this is the chain. All these derivatives in the book are the chain rule. So what we really have is 1 divided by the natural log of a over u times u prime of x. This u prime is the chain part of the chain rule. So for our particular problem, you take 1 divided by the natural log of whatever the base is, which is 5, times u, which is going to be the argument. That's the argument of the logarithm, so that's going to be the sine of x. And then you multiply that by the derivative of the argument. The derivative of the sine is the cosine. So u prime of x. In this case, u of x is equal to the sine of x, and u prime of x is equal to the cosine of x. So you end up with that, and you go ahead and rewrite it as the cotangent. So it would be the cotangent of x divided by the natural log of 5. So it's just a matter of using the right formula, realizing that this version in the book is that the u prime is always just the chain rule. And if the argument is just x, then u prime is 1, and you just change that to 1. But if the argument is other than x, then you have to use the chain rule. Okay, so that's it for logarithms. Give you a little more practice there. I have another handout, but I didn't bring it in today because I forgot to. So we're going to start on those problems. These are the inverse trig function problems. So I'm going to pull that up, and then I'll hand it out tomorrow. So you might want to write down the solution on your paper today, but we'll continue more of these. So we have first inverse trig problems, we have more difficult inverse trig problems, and the most difficult inverse trig problems. So we're going to start off with the first inverse trig. Now, if you have your, hopefully you have this, okay? So pull that out because you can use, all we're basically doing for the first three problems is just using the chain rule and the formulas that are in your book. So hopefully either you or the person next to you has a copy. I have one copy or two copies I can lend to somebody. If you don't have anybody next to you that doesn't have one, do you guys, so you can share one? Can you share that with anybody? No? Okay. So I'm looking for people that don't have a neighbor that has the copy. Anybody else? Kristen. Okay. So all you have to do is look on the first page and look for the arc sign or the inverse sign. Look for the equation for the derivative, and then use the chain rule. The same with the second one. Look for the equation for the arctangent, and then use the chain rule. And finally, for the arcsecant. So it's not rocket science there. It's just a matter of finding the appropriate formula and using the chain rule. Whether you want to use the chain rule the long way or just use your brain, that's use your brain. How do they do it? Do they do arc sign? Yeah. Okay. So you don't have to reinterpret it or anything like that. So there'll be some, I know there's at least one problem like this. I think I've already made up the test. But it's just a simple case of looking up the formula and using the chain rule and making sure you plug in. It ends up looking kind of complicated because you end up with u squared, and u can be, in this case, u is pretty simple, but you could have u more complicated. So you still sick, Caleb? Yeah. What do you got?
I don't know.
Your dad's a doctor. What do you? I'm not going to see him. He can't even diagnose you. Just kidding.
I mean, I don't know. He just said I'm probably. He said, you're fine.
You're fine. Yeah, right. That's right. You're not dying. Yeah, some virus. So, what is u? U is x squared, right?
All right.
And so you just look up the formula here for the derivative of the arc. What is that? Sine? Cosine. Arc sine. So we look here, arc. Where is arc sine? Okay, so there's arc sine. So it's just going to be u prime. This is the chain rule. What's u prime? 2x, yeah, divided by the square root of 1 minus u is
X squared.
So you square x squared, so it'll be x to the fourth. So it'll just be 2x divided by the square root of 1 minus x to the fourth. Okay?
Right.
Oh, is Romeo still looking for his copy there? Can you guys, anybody share one with him if you have one, if you and Caleb have one, you can work off of that. Teamwork. Oh, I need to copy that over. Where's my camera? So I'm going to give you the answer, and you're going to figure out how I got it. Oh, that's the wrong problem. What am I doing here? Okay, so that's the first one. So again, you're supposed to figure out if I got that or if you don't understand. Yes, Lizzie. What's that? Well, if you rewrite x square root of x as to the 1/2 power, when you take the derivative of x to the 1/2, you get 1/2 x to the minus 1/2. So it's from that 1/2. Do you see what I'm saying? It's 1/2 times x to the negative 1/2. It's you take the old exponent, which is x is 1/2, so you multiply it by that. That's where the 2 comes. So this is really this is a half, and this is x to the minus 1/2. I'll come up and talk to you. So let me see what you did. Okay, yeah, so the derivative, remember you take, it's the derivative of x to the n is n times x to the n minus 1. So this has to be multiplied by a half, the power rule. Just like, you see?
yeah.
Yeah, okay.
So that's, okay.
Yeah, that's where it comes from. So, yes, and then yes. The second problem is actually a good example. Whoa, sorry, is a good example of where you would have a problem that may not initially look like you could use the inverse trig function. So if I said what's the integral of 1 over the square root of x times 1 plus x, you would not initially think that would fit 1 over x squared plus 1 plus x squared, or a squared plus x squared. But and we looked at a case where, we had something to the second power or fourth power, I think it was 1 minus x to the, like this one. Again, going the other direction, you might not think this is 1 minus, or a squared minus u squared. But if you take the square root of this, which is x squared, that would be u, so this would be u squared. So if u is x squared, then the derivative is 2x. So we did a problem like that, and the same thing applies here, is that, it doesn't have to be, sometimes you have x by itself, which ends up being the square root of x quantity squared, and you can make things work out. Okay, and then the last one is this, and this is a product, so you have to use the product rule. So I would actually probably just rewrite it as h of x, just so I can use the product rule. So I would let f of x would be equal to x, and g of x would be equal to the arc secant of 4x. And then we would take the derivative of each part, and the second part, you would have to use the formula. And so if you look at the formula in the book, it probably says u prime divided by the absolute value of u times the square root of u squared minus 1, something like that. Is that right? Did I read that correctly? Is the absolute value in there or not? I don't think, no. Is it in there, in the derivative?
Yeah, it's in the denominator.
Oh, okay, yeah, so it is absolute value. Yep. So all we have to do is, so if you apply the formula from the book, you'll get u prime, which is 4, that's the derivative of that, divided by the absolute value of u times the square root of u squared minus 1. So that's g prime of x. U prime divided by the absolute value of u times the square root of u squared minus 1. And then the final answer, h prime of x, you'd use the product rule, which would be this times that, 1 times the arc secant of 4x, and then you'd have plus f of x times g prime of x, so we'd have 4x divided by the absolute value of 4x times the square root of 4x squared minus 1. And the question is, can you do anything here with the absolute value? Could we simplify that? And probably we could. You still have to have the absolute value. Well, no, I'm not sure if we could or not. So I'm just going to leave it that way. Okay, so just be able to use the chain rule to use the formulas that are in your book. Okay, now moving on to the next part. These should be reasonably easy because we're just plugging numbers into the formula. So I'm not spending a lot of time on those. And then these three are just, again, they should fit the formulas exactly because we don't have, this is x squared is going to be u squared, or u is going to be x. So these you should be able to just read the formula out of the book and give the answer. You may not believe that, but let's just do that. I'm trying to leave enough time tomorrow so that we can do more difficult ones. So the only thing you have to do really in these problems is identify u and a, and then rewrite it. So in this case, we would let u squared equals x squared, a squared is equal to 49. So u is equal to x, and a is equal to 7, and du equals dx. So the original integral would just become 5 divided by the square root of a squared minus u squared du, which is, you look in your formula, and we take 5, and it's going to be the arc sine of u over a plus c, and in this case u is x and a is 7. So if I were looking at it, I'd say, okay, a is 7, u is x, so the answer is 5 times the arc sine of x over 7 plus c. If you feel comfortable enough knowing what you're doing, you don't have to go through the whole thing of identifying u, especially in this form, where you have a clear a squared and you have a clear x squared, which is u squared. So the next one, the only difference between the next one is I don't have a perfect square, and it doesn't really matter. What I'm expecting you to do is if you don't have a perfect square, just show it as the square root of the whatever number. So over here, I've got the square root of 49, but because the square root of 49 is a integer, then I use that. But if it's not an integer, then I just leave it as the square root. So you would say a squared equals 34, a equals the square root of 34, and u squared equals x squared, u equals x, du equals dx. And so the original integral, I'm going to pull the 7 out front. So you can have 7 divided by 1 over a squared plus u squared du. So now it fits the book exactly. And you go look in the book, and it says the integral of this is 1 over a times the arc tangent of u over a plus c. And then we just plug the values in. So a is the square root of 34. U is x. A is the square root of 34. And you add c. And you would move the square root to the numerator by multiplying both the numerator and the denominator by the square root of 34. So you've done this before. Arctangent. And you do the same thing in the radical. So you'd have the square root of 34x divided by 34 plus c. So those are trivial. I think I have one of those on the test. You know, just a simple inverse trig, an integral involving the inverse trig functions, where all you have to do is identify a and u and plug it into the formula. And let's just go ahead and do the last one. So this is an inverse. This is the arc secant. So in this case, it's not, you know, a u is not exactly x. So what you would have is you would have u squared is equal to this thing, 4x squared. So u would be 2x instead of just x. So that's what happens if you ever have anything other than just x squared. You just have to say this whole thing's u squared, take the square root of each part and get that, and then you get du. So you get this extra factor of 2 in there that you haven't seen up to this point. A squared is 16, so since that's a perfect square, we can write that down as a number. So with all that taken care of, we can factor out the 12. So we get 1 divided by, so x is u over 2. So if we take this and we solve for x, we get x is u divided by 2. So instead of x, I put u over 2. And then I have the square root of 4x squared, which is u squared, plus 16, which is a squared, and all times du. So that's one difference. In the arcsecant thing, a lot of times we think dx over x somehow has to be du. But because the original integral involves u outside here, we have to do these 3 substitutions. And dividing by 2 in the denominator is like multiplying by 4. So I'm going to go ahead and take that out completely so it matches what's in the book exactly. So I get that, and I look what is the integral of that. It's equal to 1 over a times the arc secant of u over a plus c, because that matches up exactly. So I get 24 divided by a, which is 4, times the arc secant of u, which is 2x, divided by a, which is 4. So I'm just plugging back in now to get in terms of x. So 24 divided by 4 is 6. So I get 6 times the arc secant of x over 2. So I go ahead and simplify these fractions if I can. And that's the final answer. So we're done with that one. So what we'll do tomorrow is we'll do the next more difficult. Whether we'll get to the most difficult, we probably won't get till Friday. So the only thing the next part is where you have to complete the square. Your original denominator does not match exactly the formula, so we've got to massage it so it does. So that'll be tomorrow. We'll have that on the test. And then Friday we'll do the most difficult one. So you can turn both of those papers in today if you haven't done. Hopefully you did. And I'll hand it back to you tomorrow. Yep. Yep. So the two that we did today, if you want to hand those in, then I'll hand it back to you tomorrow.